Hi, my name is Jim, and our topic is inductors, which have characteristics which are very similar but opposite to that of capacitors. And an inductor is based on a magnetic field, where a capacitor is based upon an electrostatic field. We very briefly here take a look at a wire, and this would be, say, a wire cut in half, and we have a current flowing through it. If the wire is perfectly circular, at the very center of this, a magnetic field, an H field of concentric lines, will begin and grow first inside of the wire and then external to the wire. And the size of the magnetic field is determined by the current flow through the wire. Now, starting on the inside of the wire here, may not seem to be eventful, but at high frequencies, what this causes is the effective area, cross-sectional area of the wire, decreases because current is impeded in the center of the wire due to the magnetic flux. Now, that's a topic for later on, but just thought I'd mention it going into this. Capacitor stores energy in an electrostatic field, and the energy it stores is 1/2 CV squared, and the unit on that is the joule, which is a 1 watt second. Not 1 watt per second, but watt second. Inductors store energy in an electromagnetic field, and its equation is somewhat similar. The energy stored is 1/2 times the inductance times the current squared, and again, its units are the joule. So this here is potential energy. Last video I charged capacitor and walked around and then put a light emitting diode upon it. And an inductor stores energy in a kinetic field, which means as soon as you take the power source away from an inductor, the magnetic field begins to collapse immediately. And the rate of collapse is determined by the time constant of the circuit. So we'll get to that in a second. The unit of measure of inductance is the Henry, where in capacitors it was a farad. And a Henry is defined, and this is a rather difficult concept to see, that if you have 1 ampere per second change flowing, this is change flowing through an inductor, it'll produce a 1 volt drop. Now, what does a 1 ampere per second, I'll call it a signal, look like? This would be time, and this would be current, and that is changing at a rate of 1 ampere per second. So physically, picturing a device that can do that would be difficult. It would take multiple components and so forth to do it. But the magic term here is Henry, and like the farad, it has subcategories: millihenries, thousands of a Henry, microhenry, and so forth. Never seen anything with a kilohenry, so that's huge inductor, but I've never seen that anywhere. So if we take a typical circuit here, and we have our battery and a switch, and in this case a 220 ohm resistor and a 400 millihenry inductor, and close the switch, current is going to begin to flow, and the inductor is going to be charged, and sometimes that's referred to as fluxed. So in this, I'm going to use fluxed and charged interchangeably. And how much time does it take for that magnetic field to build up? And this is very similar to the case of capacitors, where we were talking about how long does it take for the electrostatic field to build up. So the time constant, again tau, and again the unit of this is going to be seconds, is equal to the inductance divided by the resistance. And that may seem to be a strange relationship, and a little bit more challenging to understand, I think, than the RC circuit. So basically, if we had an inductor, say a Henry, and a very, very small resistance R, we could have with a time constant of 1 second, then in your mind's eye picture this magnetic field collapsing and being 66% of what it would be in 1 whole second. So it slows down as R gets smaller. The collapse of a field would slow down. And likewise, when we're charging an inductor, fluxing it, the rate at which that magnetic field grows is also equal to L over R. So all of the time constant material that we talked about before is applicable here, but as I said before, the inductors has characteristics which are opposite to that of a capacitor. So let's take an example here. Find tau, and in our circuit here we have a 220 ohm resistor and a 400 millihenry inductor. And just using the math for the time constant, we see that comes out to be 1.818 milliseconds. So what that means is when the switch closes here, 1.8 milliseconds later, the inductor will be approximately 63% fluxed. Now, when the current starts to flow in this circuit, it builds a magnetic field that cuts the wire, and it produces a counter EMF that opposes the current flow. And that very fact, which we'll explore in detail, I want to mention it now, is why the current just doesn't grow instantly to final value. So, in AC circuits, this phenomenon will be referred to as inductive reactance. And actually, it's a counter EMF, counter voltage, which is formed in the inductor by the growing of the field. So anyway, the inductor is fully fluxed after 5 tau, just like a capacitor, and that's also asymptotic, but the industry says that it's fully charged after 5 tau. Physically, a wire has inductance, and that's any wire. And we saw that in the capacitor diagram of a real capacitor with ESL, effective series inductance, and that's just the wire leads associated with the capacitor. So all wire has inductance in it. And sometimes in your home, in the dark, if you turn off lights or something, you might see a flash from the switch plate. And what that's caused by is the inductance of your house wiring is collapsing. And as we'll see later, it induces a relatively large voltage because the stored energy in the magnetic field has to go somewhere, and it arcs across the switch. So depending upon the color of your switch and the color of your wall plate, you from time to time may see that. Not every time. It depends on the current at that time. And in an AC circuit, which your home is that current varies from 0 to maximum 120 times a second. Let's see. Now we have inductance here in henries, and we're going to be talking about a coil of wire. And all that does is that we have wire next to wire, so these growing magnetic fields of each wire tend to support each other, and you get an additive effect on it. And what it depends upon is the number of turns. So the more turns you have in an inductor, the higher the inductance, measured in henries. The diameter of the wire, so the larger the diameter, the higher the inductance. The length of the inductor, and surprisingly that's an inverse relationship. The longer it is, the lower the inductance. When you think about it, if you have a long inductor, the magnetic field formed by the wires at this side would not interact and support the magnetic wires and the magnetic lines formed by the wires at the other side. So you don't get that additive effect as if you had a short inductance. And fourth is the core, and that's the material inside the coil of wires. And we'll look at that now. So the inductance is related to the core permeability times the area divided by the length. So this is kind of a constant here. And first we're going to look at an air core transformer, and that's many times used in radio frequency circuits, meaning high frequency circuits. And we're not going to talk about the relationship of inductance with frequency here. But if we take a piece of steel which has a high permeability and insert it in this coil, what we will see is that the inductance increases dramatically. So you have different types of cores that you can insert in there. Some are powdered iron and so forth, which can vary the inductance of the circuit. Now, early car radios in the 60s, when they got into push buttons, actually had 3 of these coils, and when you pushed the button, you mechanically inserted a core. And what that would do for those car radios would change what's called a resonant frequency, and that's how you were able to use push buttons to set your channels. And it was a mechanical system of pushing cores in and out. That's the only reason why I mention it. So ferrous cores may seem like a really good thing, except they have some bad attributes to them. And if we just take a look at kind of like a voltage and current plot, and here we have the H, which is called the magnetizing force, and here we have B, which is called the flux density, or flux per unit square centimeter. As we see that as current starts to flow through the coil, is that the flux per unit area builds linearly, and then it reaches a point where increases in the magnetizing force will not produce corresponding increases in the flux density. And that's called saturation. It's a nonlinear effect, and depending upon the application, it could be a bad situation. Generally speaking, you do not want things to saturate. Further, if you reduce this, now we're going to reduce the magnetizing force, and you think you'd end back up at the origin, but you don't. You end up over, in this case, here somewhere. Let's see, coming down, yes. So what we end up with is a slight permanent magnet after we would do this to something with a ferrous core. So the permanent magnet part of this may be good, that's what you want to make, and it may be bad if you're working with this in a circuit, because you have to apply a magnetizing force in the other direction to get the flux back to zero. So that's just a very quick overview of some of the disadvantages of using a non-air core. Air cores never saturate. You can always put more flux into a core where the amount of flux, magnetic lines of force, that you put into a steel core or metal core, ferrous core, is limited. So let's take a look at the charging waveforms here, and what we have to do in this case, like with the inductor, is we have an initial condition. You know, we were, in case of the capacitor rather, when we talked about capacitors, we said that the DC at time equals 0 and charging would always be equal to 0 volts. Now the same is true with an inductor. We're going to say that there's no flux in it prior to closing the switch. So that makes our calculations a little bit easier in an inductive circuit, other than most supplies that typically would not be something we're going to consider. So what happens here is that t equals 0 plus is the switch closes, and surprisingly the voltage across the inductor jumps up to the supply voltage 10 volts. Now in a capacitor, if you recall, it started at 0 and began to increase asymptotically approaching 10 volts. Now what's going on here is when you close the switch, current starts to flow, that magnetic field builds up, opposes the source, and all of the voltage at t equals 0 plus is across the inductor. And then as the current begins to flow, is that voltage across the inductor decreases. Now if we take a look at the voltage across the resistor, what we see is that it initially starts out to be 0. And the reason is because all of the voltage is across the inductor. So as time passes, the voltage across the resistor asymptotically approaches 10 volts. Now the shape of the voltage across the resistor is also the shape of the current, due to the fact that resistors are linear and Ohm's law applies. Now if we add these two voltages together at every single point in time, it has to be equal to 10 volts, and that is a function of Kirchhoff's voltage laws. So one of the things, and we'll have a summary page a little bit later, to remember is kind of the opposite situation, where a capacitor and an inductor have very, very different characteristics when it comes to initially starting to charge them. So let's see here. We know we have a time constant from the previous example of 1.818 milliseconds. And let's work a problem where we're to find the voltage across the inductor at t rather, not tau, t equals 2 milliseconds. And since this is a decaying exponential, we would use the decaying formula with that. And that would be V inductor equals the source voltage times e raised to, guess what, negative t over tau, same as capacitors. And working this out, we're interested if time equals 2 milliseconds, and the negative means that it's a decaying function, it's an asymptote, or if that were a positive exponent, it means that the voltage would grow without limit. So that's, when you see the negative up there, you know it's going to be a stable circuit. And then I've put down the intermediate value for e raised to the power of t over tau, and that comes out to be 0.332. And what we find at 2 milliseconds is that the voltage across the inductor is 3.382 volts. So this would be a projection here, and you see that 2 milliseconds is more than 1 tau here by a little bit. And then projecting up and off of the characteristic curve of this gives us our 3.328 volts. So let's find the current at 2 milliseconds, and what we know about the current from the previous page is that it's a rising asymptotic relationship. So here we have the 1 minus E involved with that, and substituting in our values here, well, first we need to know what Imax is. We have to start there. So in an inductor, after 5 time constants, the voltage across it is considered to be 0 volts. Now, what that means is all of the voltages across the 220. Therefore, we can simply use Ohm's law and determine that the final current, the maximum current that can flow in the circuit after the inductor is completely fluxed, is 45.45 repeat milliamperes. So what we'd use to find the current then is this would be our Imax value, same asymptotic approach, and what we end up with is a maximum current of 30.32 milliamperes. I shouldn't say maximum current. This would be the current at 2 milliseconds. So that's not too hard to find. And when you look at these, if the curve is falling, you use this formula, and if the curve is rising, you use this formula. And if we have any initial voltage across capacitor or flux into inductor, we would have to take that into account, but that's not our purpose here. So we can find VR, the voltage across the resistor at 2 milliseconds, and I've elected to do it verbosely here. Since it's going to be a rising exponential also, end up with basically a similar equation, except here we have the voltage, and that gives us 6.68 volts. So the voltage across the resistor can also be found without using exponential, just by the relationship of KVL, in that the total voltage has to be equal to the sum of the voltage across the inductor plus the voltage across the resistor. So if I want to find the resistor voltage, I just subtract the capacitor voltage, which we determined up here, from 10 volts, and that gives us 6.672, which compares favorably with the 6.68 that we obtained by using the more verbose exponential form. Likewise, if we know the voltage across the resistor, it's an easy matter to find the current through it, simply using Ohm's law here, and that comes out to be 30.33 milliamperes, which favorably compares to the more involved exponential form to get that. So any way you want to get the parameters is fine, but for sure you have to start out with finding the voltage across one component. And then by working KVL and Ohm's law, you can basically find out everything else. So which is the right thing to do? Whatever easier. Whatever's less prone to error. And accuracy, well, our resistors here, tolerance is typically 5%. Inductors that we use are 10%. So small variations in voltage like this really become insignificant because of the tolerance, and that tolerance is also a function of temperature. So in summary here, we're going to start out with our RC circuit, and over here we have our RL circuit, and the charging of the capacitor here, as we saw before, would be at 5 time constants. We see that the capacitor voltage would approach the source voltage V, and when we're fluxing the capacitor and the switch is closed, we see that the voltage across the inductor is maximum, V, and exponentially decays, and at 5 tau is considered to be 0 by the industry. Contrarily, VR in a RC circuit starts out to be at V, and that's because VC is 0, so all of the voltage of V has to be located across the resistance. So the voltage here and the voltage here has to equal the voltage here per KVL, And as the capacitor voltage grows, the resistor voltage drops. In an inductor, again, the sum of these two has to be equal to V, since all the voltages across the inductor is zeros across the resistor. So as time passes, the voltage across the inductor drops, the voltage across the resistor rises, and then at 5 tau is considered to be equal to V. That would be the voltage across the resistance is equal to V. So we always have to remember that the sum of VC and VR equals V, and the sum of VL plus VR equals V. So KVL is a very important law that has to be kept when we're looking at this. Now, if I were to ask what the current would be in both cases, it would have a shape like this, and then we would have to scale it depending upon the voltage in the case of capacitors, and the maximum current like we did before in the case of inductors. So let's take a look at discharging. And in DC, what we would be doing then, and this would be the circuit, and what I've got here is a single pole double throw switch. And what I have to say about that is it takes 0 time for me to move the bat on the switch from this position to this position. And the same with this. So when you see a single bat and a single common, I guess it will, and 2 poles out here, it's single pole double throw, abbreviated SPDT. And this would be, just for familiarity's purpose, a 3-way switch in your house where you can turn lights on and off from 2 locations. Would be a switch like that. So in the case of the capacitor, is when we flip this down, we have the voltage across the capacitor being plus, and basically it flows through the resistor and discharges the capacitor, and at 5 tau the capacitor is completely discharged. We'll say 0 volts. Now in the inductor we have kind of a strange thing happening, is that the voltage across it tends to go negative, and then it exponentially decays. Now what's that about? Well, if we take an inductor here, and this is what I'm doing here, is expanding on a Y, that this is has a component in the 4th quadrant, is when we're fluxing it, we have the switch in the up position and current is flowing in this direction as we would expect it to. And we say we'll have a plus to minus drop across the resistor and a plus to minus drop across the inductor. And then what will happen if we flip that switch, and this is the key difference between inductors and capacitors, is an inductor is like a flywheel. It doesn't want to see current change. Capacitor is the opposite. It doesn't want to see voltage change. So we have this magnetic field stored, and when we flip the switch here, that field collapses. Now when you think about it, when we charged the inductor, the field was growing, and it induced a counter EMF in the inductor, which gave rise to the exponential shape of that, starting out at our 10 volts for finding VL and decaying. Now when the switch is flipped in the opposite direction, where it has a discharge path, that field is no longer growing, but it's collapsing. And what that does is it switches the voltage across the inductor instantly, and the discharge path is in the same direction through the inductor as the charge path, except the source of energy is now the magnetic field of the inductor. So when you're dealing with discharging, if you just reverse the signs of the voltage across the inductor, you can get a pretty good idea of the way the current flows. So the core of this is that inductors want current to remain the same and capacitors want voltage to remain the same. Now when we charge this here, is what we see now is relative to ground, the top of the inductor is now negative, hence down, and then it exponentially decays. So that switching of polarities is why the current flow in a discharging cycle is in the same direction as the charging flow, where in a capacitor, if you remember, that the discharging current flow was in the opposite direction to the charging flow. Taking a look at the voltage across the resistor when a capacitor is charging, that would be when the switch would be in this position, is what we would find, this is the capacitor circuit, is that the voltage across the capacitor from last time would be equal to 0 volts, and hence the voltage at T equals 0 plus would jump up to the capacitor, the supply voltage rather. Let me get rid of this here. And then exponentially decay as the capacitor became charged. Now, when the switch is flipped down to this direction, and do notice that the defined current flow is this way, charging the capacitor. When the switch is flipped down to here, the capacitor now becomes the source of the energy, and it discharges in this direction through the resistor, which is counter to the defined direction of current flow. And as a result of that, the voltage would be starting out at negative VC and exponentially decaying to 0. This would be across the resistor. Now, in both the case of the inductor and the capacitor, there's a fourth quadrant excursion in both of these. A little bit different reasons why they're there, but that's just a fact of life. Now, how do you find out what's what? And first you have to know how the part operates. The capacitor starts out at 0 voltage and charges up to the source. An inductor starts out at 0 current and all of the voltage is across it, and then the voltage will grow across the inductor as time passes. When you get the fundamental operation of the capacitor and inductor down, and you know how to use KVL and the two charging and discharging exponential equations, you can figure out anything. So let's just look at a phenomenon here, which is referred to as a transient. And transient means it's a relatively short time period phenomenon. It can be current or voltage, or both, or for that matter, power or energy. But the inductor has a relatively unique characteristic that capacitors do not have. So what we're going to do is we're going to charge an inductor, and in this case we're using a real-world inductance. And the difference is that there's winding resistance because, well, wire has resistance and it's wound around the core, and the physical inductor is going to be a combination of both of these that I've indicated with a dotted line. And you cannot segregate the winding resistance out of it and end up with a perfect inductor. The inductance and the winding resistance are part and parcel of the same physical part. So when we close the switch here, what we'll do is examine the time constant for charging, and it's simply going to be the L in series with the winding resistance. And a good example of this would be the core of a relay, which is basically an electromechanical switch. And what we see is tau then would be equal to 200 millihenries divided by 50 ohms, which gives us a 4 millisecond time constant for the charging circuit. So when all said and done, what we would have would be our voltage 10 volts appearing across this part, and if we could, we can't, but if we could actually look at the voltage across the resistor, we would see that it would be 10 volts. But since this is integrated, it's across the entire part. So what we would see here is that if we looked at the voltage across the winding resistance, as I had said, is we would see that that would grow exponentially toward 10 volts, and the voltage across the inductance would exponentially decay. I should say exponentially asymptotically grow and asymptotically decay, but we can't look at that, so it's just kind of what's going on inside the part, I guess you could say. So after 5 time constants, the current flowing through this device here would be simply 10 volts divided by 50 ohms, which would be 200 milliamperes. So what we're going to do is leave this on for at least 5 tau, and then we're going to open the switch. And notice that this is not a single pole double throw switch, it's a single pole single throw switch. So there's no discharge excepting through this 1K resistor, which is in parallel. Now the only reason this 1K is here is to demonstrate the transient effect. So what we know about this at T0 plus when the resistor opens is that 200 milliamperes at that time instant is going to continue to flow. The voltage across the inductor changes polarity to keep the current flowing in the same direction, and the discharge path now is through that 1K resistor. So what we want to do is find out what the initial voltage drop, and that's at T0 plus, and that would simply be 200 milliamperes times 1 kilo ohm, and doing the math on that, it turns out to be a whopping 200 volts. Now what's important to note is that this side of the resistor is anchored to ground. So if we actually look at the voltage at this point, and I've designated that with the label V sub L, is what we would see would be something very interesting, and we could say that this side of the resistor would be more negative than this side. So what we can expect on the opening of the switch is we would have a negative going transient. So let's find out what the time constant of the discharge path would be. Now the charging path was simply this, but the discharging path includes the additional 1K resistor. So that would be our 200 milliamperes inductance divided by the total resistance, which would be 1050 ohms, including our winding resistance here. And that gives us a time constant which is much smaller of 190 microseconds. So we're dealing with two time constants here. So if the circuit's been turned on for a long time, is what we would see would be the part, this guy would have 10 volts across it, and then when we open the switch, this negative 200 volts would take effect, and we'd get down to negative 200 volts, and then we would exponentially decay, and at 5 time constants, and this is 5 time constants, discharge would be equal to 0 volts. Now all of this happens very quickly compared to the charging time, because the time constant of the discharging circuit is very much quicker. So at 5 tau, what we have for the discharge would be 950 microseconds, and then the 5 tau for the charging circuit would be 20 milliseconds. So basically, to make sense out of this, is if the time constant is smaller, the energy has to be dissipated quicker. And that's why you get this. Now, what would happen if we made that 10K? Essentially, this would go down to negative 2,000 volts. I might say this is crazy, and it might seem like that. The time constant would be even narrower still. It would have a characteristic maybe which would be coming up from the floor, and time constant wise would be looking something like this. So again, that energy would have to be discharged faster. Now what happened if we didn't have a resistor here? What would the discharge path be? Well, the polarity would be this, and even though the switch is open, current would flow through it. How does that happen? It arcs across the switch. The time constant in that case would be very, very small, and the voltage then would be very, very high. Most likely we get an arc. Whenever we have an arc, we move metal, and that's bad, because switches wear out, relay contacts wear out, and so forth. Now where this really plays well is in making spark plugs work in your car, and that's just based upon charging an inductor, opening a circuit, and letting the discharge path produce a really high voltage, which causes a spark across the electrodes in your spark plug, which hopefully is around a gas-air mixture which is favorable to ignition. And it's not 100% guaranteed that a spark is going to light off a cylinder. So that's the transient nature of induction and inductors, and if I were to have my finger across this guy, when I open the switch, I would definitely feel it. The 200 volts would definitely be able to penetrate the dryness of my outer layer of skin. So that'll conclude for inductance, and thank you for watching.